A huge compound horseshoe magnet with two pole pieces to concentrate the field. An electrical conductor passing between the poles of the magnet. And as the disc, the conductor, is turned, a continuous electric current flows through the galvanometer circuit. This was the very first dynamo. The date was 1831, and the man who made it, Michael Faraday, known as the father of electricity. His discoveries led to the dynamos and transformers that give us the light and power we need today. It was here, at the Royal Institution in London, that Michael Faraday worked. For nearly 200 years, the Royal Institution has been associated with scientific research and education. Inside, many of the showcases contain apparatus used there in important discoveries in science. Prominent among them are those used by Faraday himself and by Sir Humphrey Davy, his predecessor as director of the Institute. Today, the present director, Sir Lawrence Bragg, maintains this great tradition. He is giving one of a series of lectures to school children, which were inaugurated by Michael Faraday, and he is performing one of Faraday's own experiments. A Whimshurst machine, this giant one was built by Whimshurst himself, is being used to charge a wire cage. It's known as Faraday's bird cage. Strands of silk are forced away from the cage, but the charge has no effect at all on the girl inside. Faraday performed this experiment as part of his investigation into the effects of lightning. It showed that there is no electric field inside a hollow conductor. When the girl puts her head through a hole in the cage, the tinsel of her crown and wand are affected, but she is safe, as long as she touches nothing outside it. To render the cage harmless, it must be discharged. Among the many eminent men to lecture here was Sir Humphrey Davy, inventor of the miner's safety lamp, and it was to some lectures of his that Michael Faraday came. At that time, it was 1812, during the Napoleonic Wars, Michael Faraday was unknown, a young man of 21 working as an apprentice bookbinder. He had left school at the age of 12, and he first became interested in science when, in his spare time, he read from a copy of the Encyclopedia Britannica that a customer had brought in to be bound. From this book, and from the lectures at the Royal Institution, he learnt as much as was then known about electricity and magnetism. The subjects were little understood. They were thought of as mysterious fluids with magical qualities.
The phenomena of magnetism, like those of electricity, depend on a cause so little subject to the investigation of our senses that any regular and well-supported theory can as yet scarcely be expected.
Magnetism had, of course, been marveled at for centuries because of the lodestone, a lump of iron ore with magnetic properties. It was known that when a lodestone is rubbed along the length of an iron rod, the rod becomes a magnet and has the same properties as lodestone. When suspended, a magnet points, like a lodestone, to north and south, and it has the same properties of repulsion and attraction. Like poles repel each other, unlike poles attract. Iron filings can be used to show the magnetic effect around a magnet, the magnetic field. The pattern led Faraday to refer to lines of magnetic force. The arrows show the direction of the magnetic field, the direction in which a north pole would move if it were free to do so. In this experiment, the south pole end of a magnet follows a path from one end to the other of a bar magnet beneath it. Another form of attraction, known since ancient times, is that which we now call static electricity. When a piece of amber, or a glass rod, is stroked with silk, it becomes electrically charged. The rod is able to attract small pieces of paper. Later, the rubbing was done mechanically, as in the glass friction machine. It produced enough static electricity to store a Leyden jar. But this was very little, and the jar had to be continually recharged. Bells could be made to ring and other comic effects achieved, but static electricity could be put to little practical use. Then, in 1800, the Italian scientist Volta made the first electric battery, a pile of silver and copper discs separated by leather soaked in brine. For the first time, a source of electric current, small but steady and continuous, was available. It was soon used in experiments. Water could be decomposed into its elements. And using improved batteries, like these, Sir Humphry Davy discovered new elements, sodium and chlorine. He also invented the arc lamp, the first electric light. These new discoveries fired the imagination of Michael Faraday. He determined to become a scientist himself. He wrote out notes he'd made at 4 of Sir Humphry Davy's lectures. These he bound into a book which he sent to Davy at the Royal Institution, with a letter asking for a job. Also preserved at the Royal Institution are the diaries begun by Faraday in 1820. They record a remarkable contribution to the development of science. Faraday started as an assistant to Davy at the Royal Institution, but he soon established a reputation as a great and original experimenter. Since Volta had made his first battery, interest in electricity had been intense. But it was not until 20 years later that a Dane, rsted, found that a current flowing in a wire would deflect a magnetic needle. He had discovered a direct connection between electricity and magnetism. Throughout Europe, a new wave of discovery began. Ampere, Biot, Laplace, and Arago all played a part. Ørsted's experiment changed everyone's ideas about electricity. In England, on the day that a translation of Ørsted's work came into his hands, Faraday confirmed his results. The current flowing through the wire had a definite effect upon the magnetic needle. There was clearly a direct connection between electricity and magnetism. The needle was deflected from its stationary north-south position. The experiment aroused Faraday's curiosity. Somehow the current must be creating a magnetic field around the wire. Another experiment showed that the lines of magnetic force were circular around the wire. This is why the North Pole in Ørsted's experiment was deflected. Like these compass needles, it would try to follow the lines of force. What would happen, Faraday asked himself, if the North Pole were completely free to move? He placed a magnet in a beaker. The South Pole end was fastened to the bottom by a fine thread. He then filled the bowl with mercury, so that the magnet would float upright. The North Pole end of the magnet was just above the surface of the mercury and was quite free to move. A circuit from the battery was completed by a vertical wire just dipped under the surface. When the switch was closed, the pole should follow the lines of force around the wire. He was right. A few days earlier, he'd established the opposite. A current-carrying wire will rotate around a magnet. These experiments Faraday performed with simple apparatus, yet he had, for the first time, made electricity produce mechanical motion. This was the beginning of the electric motor. In his diary, he wrote, "Very satisfactory, but make more sensible apparatus." In fact, he never did, for over the next 10 years, he had other work to do. During this time, the electric motor was developed into an efficient machine. Rapid progress was made by the Belgian, Gramme, and many others. The great French scientist, Ampère, evolved theories of electromagnetism which guided all the scientists working in this field. It was Ampère who showed how the magnetic field was affected when a current-carrying wire was bent into a coil. The coil behaved as if it were a bar magnet, with a north and a south pole. Also, as Sturgeon had demonstrated, a soft iron bar within a current-carrying coil was temporarily magnetized and became, in fact, an electromagnet. In 1831, 10 years after his discovery of the principle of the electric motor, Faraday returned to his work on electricity and magnetism. He had corresponded regularly with Ampère, and it was Ampère who taught him to see a bar magnet and a coil as being, in certain circumstances, interchangeable. But a new problem had arisen in his mind. If an electric current could produce magnetism, could magnetism be made to produce electricity? Surely, he thought, the answer must be here in my hand. It's said that wherever he went, he carried with him a coil of wire wound on a soft iron rod. With such a piece of soft iron in a coil, and a current passing through the coil, a magnetic field would be produced. And if, with a bar magnet, he created an identical magnetic field around a similar coil, should not a current be induced in the coil? He tried this, using a compass needle, but got no result. Then he had another idea. Suppose he could use the same core for both coils. He dispensed with the bar magnet and bent the soft iron bar into a ring and wound 2 coils on it. When a current passed through one coil, the primary, the ring would be magnetized. Would a current be induced in the other, the secondary coil? On the 29th of August, 1831, he tried it out. A current was passed into the primary coil, and a magnetic needle placed north and south beneath a wire joining the ends of the secondary. If a current flowed in the secondary coil, the needle should move. But there was no deflection. No current was flowing in the secondary coil. He thought at first that something must be wrong. But what? Disappointed, he switched off. And in the instant he did so, a current flowed in the secondary coil. When he switched on again, the needle kicked in the opposite direction. This was Faraday's famous induction ring experiment. the needle was deflected one way or the other, depending on whether the contact was made or broken. The flow of induced current in one direction at make and in the other at break. Only, and only in the instant that a current began to flow or ceased to flow in the primary coil of the induction ring, was a current induced in the secondary coil. Why? He realized that when the current was switched on in the primary coil, a magnetic field began to build up, and a current flowed in the secondary. When the field was steady, the current ceased to flow. It only flowed again, and in the opposite direction, when the current was switched off and the magnetic field collapsed. He saw that a current was only induced when the magnetic field through the coil was changing. This may seem simple enough to us today, but at the time, it was a brilliant deduction. It took months of study, continual thought, and many hundreds of experiments before Faraday was able to reach this conclusion. And now, if he were right, there was an easy way to prove it. In this circuit, there was no source of electric current at all, just a coil connected to a galvanometer, a much more sensitive version of Ørsted's needle. All that was needed now was a magnetic field, a bar magnet. So simple, but it worked. Electricity could be produced by magnetism, just as magnetism could be produced by electricity. The speed with which the magnet moved determined the strength of the current. Moving the magnet in and out produced a current first in one direction and then in the other, an alternating current. As the magnet is moved, the number of lines of force passing through the coil changes. He had proved that movement was the key. But so far, Faraday had only produced momentary currents. Could the action or movement be made continuous? He attempted to do this by using a large compound magnet. Between the pole pieces of the magnet, there was a powerful magnetic field. If he could pass a continuously moving conductor, a turning disc, between the poles to cut these lines of force vertically, would a continuous current be induced? Would it be possible to take this current off through two connections, like the terminals of a battery, and into a galvanometer circuit? As the disc turned, a current had flowed through the galvanometer, a direct current. The work done in turning the disc was converted, by the aid of the magnet, into electrical energy. This was the peak of Faraday's achievement. On that day, in October 1831, a continuous electric current was generated by a machine. It was the world's first dynamo, one of the most important discoveries in the history of science. Within a few months, Pixie and Del Negro had built more efficient dynamos. Saxton, von Siemens, Edison, and many others soon made further improvements. Faraday himself was not an inventor. The development of the dynamo and the huge electrical generators of today was the work of other men. But it followed directly from Faraday's discoveries. So too does the transformer. This one steps up the alternating voltage generated to many thousands of volts for transmission through the national grid. While in substations all over the country, others step this high voltage down to the lower voltages needed for homes and industry. Other transformers adapt this voltage to special requirements. This small one raises the voltage to the 10,000 volts AC needed for a television tube. The transformer, essential for putting electricity to practical use, is a direct development of Faraday's induction ring. If there are fewer turns in the secondary than in the primary coil, the voltage is stepped down. If, as in this case, there are more, the voltage is stepped up. In this device, an induction furnace, the coil is the primary, the secondary is the metal itself. The current induced in it raises the temperature until it melts. The same principle is used in controlled thermonuclear experiments with machines such as Zeta, the huge donut-shaped torus of which looks a little like Faraday's induction ring. In this smaller machine, the primary windings can be seen clearly. The secondary induced current flows in the gas inside the torus, where temperatures as high as those of the sun can be achieved. These experiments may one day provide us with power from the many millions of molecules of heavy water in the sea. These things were the inventions of other men, but they all derive from the induction ring, the skillful hands, and the searching, persistent mind of Michael Faraday, the father of electricity.